You've probably heard it before, the claim that atoms are mostly empty space, and that if you zoomed in far enough, you'd find that over 99.99% of an atom contains nothing at all. But that idea, as mind-blowing as it sounds, is wrong, or at least deeply misleading. Because what we call empty space isn't empty at all. Rather, it's teeming with quantum activity, with jittering fields, virtual particles, and fluctuations that never truly rest. This invisible structure has real, measurable consequences. It subtly alters the energy of atoms, leaving its fingerprints on hydrogen, and it points to something extraordinary, that what we used to call nothing is actually something after all. So buckle up and enjoy the ride. To understand where this idea of emptiness comes from, we need to go back to a time when atoms themselves were just becoming real. At the dawn of the 20th century, atoms were still a theoretical idea, but the evidence was growing and attention turned to understanding their internal structure. The first serious model came from J.J. Thomson, who pictured the atom as a smooth sphere of positive charge with electrons embedded like plums in a pudding, hence the name. In this model, the atom was entirely filled, no nucleus, no internal layers, and certainly no emptiness. But that all changed in 1911 when Ernest Rutherford and his students Geiger and Marsden performed an experiment that would overturn this model. Their groundbreaking experiment involved firing tiny positively charged alpha particles at a wafer-thin sheet of gold. Most passed straight through, just as Thomson's model predicted, but a few were deflected at sharp angles, and even more surprisingly, some bounced straight back. Rutherford described it as almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. The only explanation was that nearly all of an atom's mass, and all its positive charge, was concentrated in a tiny dense central core. That core became known as the nucleus. This was the birth of the Rutherford model, a dense centre surrounded by seemingly empty space, in which the electrons were doing, well, something. It was a radically new picture, one in which most of the atom appeared to be empty space. But how empty exactly? According to Rutherford's nuclear model, the nucleus has a radius of about 10 to the minus 15 metres, while the atom itself spans around 10 to the minus 10 metres, about 100,000 times bigger. Now, if we treat both as spheres, we see that the ratio of their volumes is simply the cube of the ratio of their radii, and when we sub in the numbers, we find a ratio of 10 to the minus 15. In other words, the nucleus occupies just 1,000th of a trillionth of the atom's volume. So on paper, that leaves us over 99.99% of an atom as apparently empty space. But does not occupied by the nucleus really mean empty, or are we overlooking something deeper, something hidden in the seemingly empty space? The real question is, what is in that space? What are the electrons doing, because we haven't mentioned those yet, and what does quantum field theory have to say about all of this? The kind of physics we're exploring here doesn't happen in isolation. It relies on long-term collaborative research, most of it in universities, and supported by public funding. So when Harvard announced it was putting up $250 million of its own money after the Trump administration froze more than $2.6 billion in federal grants, the way it was reported told a story of its own. As you can see on Ground News, 92 sources have reported on this, with 76% of those sources being high factuality. Coverage of the same story looked very different depending on the outlet. Left-leaning headlines included "America's cancer research, best in the world, is in jeopardy," and "A bloodbath. Trump administration moves to terminate scores of federal grants at Harvard." Meanwhile, right-leaning outlets framed it with headlines like "Does Trump want to destroy Harvard or reform it?" and "Anti-Trump universities line up to hire pro-Trump lobbyists." Same event, completely different framing. And the problem is, if you only ever see one version of a story, you might not realise what's being left out. In a media landscape shaped by algorithms and outrage, it's easy to miss the full media picture. That's exactly why I use Ground News, a website and app that allows me to compare how different sources report the same story, showing me their bias, factuality, and what might be missing. You can scroll through the headlines, compare the language, and actually understand the shape of the narrative, not just one slice through it. If you want to make sure you're not missing critical perspectives on stories that matter, head to groundnews.com/physics or scan the QR code. By using my exclusive link, you'll get 40% off their unlimited access Vantage plan, just $5 a month, and it will help support the channel. Links in the description and pinned comment. Okay, let's get back to the physics. So if the nucleus occupies just 1,000th of a trillionth of the atom's volume, what's happening in the rest of that space? And is it really empty? Well, first, let's consider the electrons. Every atom contains negatively charged electrons, and these must be doing something in the surrounding space. They can't be stationary, because classical physics tells us they'd be pulled into the nucleus almost instantly. But they can't be orbiting like planets either. Accelerating charges radiate, and orbiting electrons would spiral inward, losing energy and collapsing into the nucleus in a fraction of a second. So how are atoms stable at all? This was one of the major puzzles of early 20th century physics, and between Rutherford's discovery and the mid-1920s, a new framework emerged. According to this new quantum mechanical framework, one didn't treat electrons as particles following definite paths, but as wave functions, clouds of probability extending across the entire atom. Physicists realised that the probability of finding an electron somewhere within the hydrogen atom, the simplest atom, could be determined by solving the Schrödinger equation. You simply insert the Coulomb potential between the electron and proton, solve the equation in 3 dimensions, and you uncover 2 profound results. First, the electron's energy is quantized. It comes in sharply defined, discrete levels. Second, each solution to the equation, each stationary wave, doesn't represent a ripple of stuff in space, but a wave of probability, a pattern that tells you where the electron is likely to be found if you look, and these patterns aren't arbitrary. They form striking 3-dimensional standing wave patterns, what we now call atomic orbitals. Each one extends over much of the atom's volume, filling space with beautiful symmetric structures representing probability distributions. And each pattern corresponds not only to a particular energy, but a specific angular momentum, a kind of quantum fingerprint. So maybe atoms aren't empty after all. Maybe they're full of these probability clouds. But here's where it gets subtle. The wave function, this spread out mathematical entity, doesn't represent a physical substance in the classical sense. Rather, it encodes likelihoods, not stuff, where the electron might be found, not where it is. And what the wave function actually is, whether it represents something physically real or just a tool for calculating outcomes, is still an open question. Some interpretations treat it as a physical field, others see it as information or possibility, but there's still no consensus. What we do know is this: whenever you measure the electron's position, it shows up as a localized point-like event, never smeared out like a fog. So while the wave function spans a large region of space, the electron itself never appears to, which leaves us with something strangely in between, a space that isn't obviously empty, but isn't obviously filled either. But even this, the wave function, the quantized energy levels, the structured probability clouds, still isn't the full picture. There's something missing, and that something is special relativity. Everything we've discussed so far has been based on non-relativistic quantum mechanics. It works well at low energies, but it doesn't incorporate the principle of Einstein's theory of special relativity. And once you do bring those things in, everything changes. Because as we'll soon see, at sufficiently high energies, even the idea of a fixed number of electrons breaks down. And we can actually see why with a simple calculation, one that shows how the single particle picture starts to fall apart when you push it far enough. Imagine confining an electron to a smaller and smaller region of space. According to Heisenberg's uncertainty principle, the more tightly you localize a particle's position in space, the less precisely you can know its momentum. And because momentum is related to energy, the greater the uncertainty in momentum, the greater the uncertainty in energy. More precisely, as the uncertainty in position delta x reduces, the uncertainty in momentum delta p must grow according to Heisenberg's famous relation. We can then estimate the energy associated with this momentum. For a relativistic particle, the energy is roughly equal to the momentum times the speed of light. And if we then sub in the momentum from the Heisenberg expression, we find h bar c divided by delta x. We see that as delta x becomes smaller, the uncertainty in energy grows. Eventually, it becomes comparable to the rest energy of the electron, E equals mc squared. At that point, the energy is high enough in principle to allow the creation of real electron-positron pairs. If we set the two scales equal and rearrange, we find that when delta x falls below about 10 to the minus 12 meters, the uncertainty in energy becomes large enough to allow the spontaneous creation of particle-antiparticle pairs. This scale is known as the Compton wavelength. It's smaller than an atom, but larger than a nucleus, meaning it lies right inside the supposed empty region of the atom. And that matters, because below this scale, the very number of particles becomes uncertain. Ordinary quantum mechanics breaks down. To make sense of this, we need a deeper theory, one that allows particles to be created and destroyed. That theory is known as quantum field theory. In quantum field theory, particles aren't fundamental, fields are. Fields that extend across all of space. The electron field, the photon field, the quark field, and more. What we call a particle is just a localized excitation in one of those fields. This is what permeates the atom. Not orbiting electrons, not classical emptiness, but quantum fields, jittering with possibility. One way to picture a quantum field is as an infinite set of coupled quantum harmonic oscillators, one at every point in space. Now, a classical harmonic oscillator is like a mass oscillating on a spring, and something you get taught in high school. But how does a quantum harmonic oscillator behave? Well, just to emphasize the point, in classical physics, an oscillator can lose all its energy and come to complete rest. Zero displacement, zero momentum, zero energy. But in quantum mechanics, even the lowest possible energy state, the ground state, still contains energy. There is no such thing as a truly at-rest quantum oscillator. Okay, so let's try to quantify this. The total energy of a harmonic oscillator can be written as p squared over 2m plus half m omega squared x squared, where m is the mass, p is the momentum, x is the displacement, and omega is the angular frequency, which is equal to 2 pi f, where f is the temporal frequency. And the first term in our energy equation represents the kinetic energy, and the second term the potential energy. But in quantum mechanics, we can't specify both x and p exactly. The uncertainty principle tells us that there's a fundamental limit to how precisely we can know both at the same time. To estimate the minimum energy, let's replace x and p with their uncertainties delta x and delta p. In that case, we find the following expression. Then, if we use the exact form of the uncertainty principle and rearrange for delta p, and then sub this into our energy expression, this gives us an equation entirely in terms of delta x, the uncertainty in position, letting us estimate the lowest possible energy purely from how confined the particle is in space. We can plot this energy function with delta x on the x-axis and E on the y-axis, and we clearly see that it has a minimum. To find this minimum, we simply differentiate the energy with respect to delta x, and if we set this result equal to 0 and then rearrange, we find that the minimum energy occurs when delta x is equal to the square root of h bar divided by 2m omega. If we then plug this back into the energy equation, we find that the minimum energy of our quantum harmonic oscillator is equal to half h bar omega. This is telling us that even in its ground state, a quantum harmonic oscillator has energy, and this energy is known as the 0-point energy, and it's a direct consequence of the uncertainty principle. Now, here's the key idea. Even in their lowest energy states, quantum fields aren't still. Each mode, like a harmonic oscillator, continues to fluctuate with a minimum irreducible energy, and quantum field theory tells us that these modes are everywhere. So even when no particles are present, no photons, no electrons, the vacuum isn't silent. Each mode jitters with 0-point motion. And it's important to emphasise, these aren't just mathematical artefacts, they're real physical fluctuations that can interact with matter, a vacuum that can reach into atoms and shift their energy. So now the task is clear. Estimate the energy shift caused by vacuum fluctuations, and then compare that to experiment. If the shift is real, then the vacuum is not empty. But to detect a shift, we first need a baseline, the energy of an electron in hydrogen without vacuum effects. We can estimate this baseline energy using the uncertainty principle. If the uncertainty in the electron's position is roughly the size of the atom, which we call A, then Heisenberg's uncertainty principle tells us that the uncertainty in momentum will be of order h bar divided by A. We can then estimate the kinetic energy of the electron due to quantum confinement by calculating delta p squared divided by 2m. And then if we sub in the momentum uncertainty, we find h bar squared divided by 2ma squared. The potential energy between the electron and proton is given by the usual Coulomb potential, and if we then add this to the kinetic energy, we get the total energy of the electron. If we plot this energy function, we see a clear trade-off between the kinetic and potential energy terms, and there is a unique separation that minimises the total energy. I've covered this in more detail in another video, but here's the gist. Differentiate the energy with respect to distance, set the result equal to 0, and you'll find that the minimum occurs at the Bohr radius, A0. And if you plug that back into the energy equation, you recover the well-known ground state energy expression for the hydrogen atom, which is equal to minus 13.6 electron volts. Okay, so now we have a baseline. That is the picture without quantum field theory. But as we've already seen, quantum field theory tells us that the vacuum isn't truly empty. It's alive with fluctuations, fields like the electromagnetic field jittering even in their lowest energy states, and these jitters extend everywhere, including inside atoms. So the deeper question is this: can these vacuum fluctuations actually shift the energy of a hydrogen atom? If they can, then the vacuum isn't just a passive backdrop, it's a physical entity with real, measurable effects. And remarkably, this idea leads to one of the most precise predictions in all of physics, the Lamb shift, a subtle correction to hydrogen's energy levels caused by the restlessness of empty space. To quantify this, we will focus on one field in particular, the quantum electromagnetic field. The electron is electrically charged, so it directly couples to fluctuations in that field, fluctuations that, even without real photons, can nudge the electron, tiny random forces that over time shift its energy. Now, it's important to emphasise that what follows is a semi-classical back-of-the-envelope estimate. It's not a full quantum electrodynamics calculation, but remarkably it captures the correct structure of the energy shift, including its dependence on fundamental constants. The approach we adopt here is a highly simplified version of a semi-classical argument first proposed by Theodore Welton in 1948 and beautifully explained by physicist Brian Skinner in his Gravity and Levity blog post. Best of all, the approach we adopt means we won't need anything more advanced than high school maths to get there. To model this effect, we need to understand the idea of modes, and to make it concrete, we can imagine placing the electromagnetic field inside a large cube of side length L. This isn't a physical box, it's a mathematical tool. It lets us impose clean boundary conditions, like requiring the field to vanish at the edges, which forces the field to form standing waves inside the box. Just like a vibrating string can only support certain wavelengths, so can the electromagnetic field, and these allowed standing wave patterns are what we call modes. If we begin by considering just a single dimension, then only certain wave patterns are allowed inside the box. Specifically, only whole numbers of half wavelengths can fit inside, like a guitar string that only vibrates in particular harmonics. If the box has length L, then the allowed wavelengths will be given by 2L over n, where n is an integer. In 3 dimensions, it's the same idea. The allowed wavelengths along each axis take the following form. Now, the wavelength lambda and wave number k are related by the equation k equals 2 pi divided by lambda. And if we apply this to our wavelength constraint, we find the following conditions on the wave numbers in each spatial dimension. Now, we can combine the x, y and z wave numbers into a wave number vector. And for each spatial mode, there's a corresponding temporal frequency, that is, how fast it oscillates in time. For an electromagnetic wave, the ordinary cyclical frequency f and the wavelength lambda are related by f equals c over lambda. And from this, we define the angular frequency, omega equals 2 pi f, which is equal to 2 pi c over lambda. And since the wave vector k has magnitude 2 pi over lambda, we can write omega k equals c times the magnitude of k, and this corresponds to the angular frequency associated with mode k. Now, in classical physics, a field mode can vibrate with any amplitude, including zero, and so its energy can, in principle, be zero. But in quantum field theory, each mode is treated as a quantum harmonic oscillator, and quantum harmonic oscillators have a minimum energy, even in their ground state, which, as we've already seen, is given by the following expression. This is the 0-point energy of mode k, the irreducible vacuum energy of that mode. And we can then combine this ground state energy with the expression for omega, and we end up with an expression for the ground state energy of mode k written in terms of the magnitude of k. And from now on, to ensure our notation remains uncluttered, we will write the magnitude of k without the bars, taking it as given that we're referring to the magnitude, and so our vacuum 0-point energy will be written in the following form. Now, according to Maxwell's equations of electromagnetism, the energy density associated with an electric field in a given mode k is given by the following expression, where E subscript k is the root mean square electric field amplitude associated with mode k. We can then calculate the total energy stored in the field mode k by multiplying the energy density by the volume of the box, which we can then write in terms of L, and if we then sub in the energy density U, we find the following expression. Next, we recall the 0-point energy we derived for mode k. To estimate the corresponding vacuum field strength, we now make a common semi-classical approximation. We equate this quantum 0-point energy with the classical energy stored in an oscillating electric field of that mode. While simplified, this approach captures the correct scaling and offers a remarkably accurate estimate of the field's amplitude. If we then rearrange this expression and take the square root, we find that the vacuum electric field amplitude associated with mode k is equal to the square root of h bar c k divided by epsilon naught L cubed. So even with no real photons, the field still fluctuates with this amplitude, purely due to quantum effects. And here's the kicker. Every allowed wave vector k, every standing wave mode that fits in the box, contributes its own vacuum energy and fluctuating field. That's an infinite number of jittering modes, even in the absence of particles. This is the essence of quantum field theory. Empty space isn't empty. It's a restless sea of vacuum fluctuations, a superposition of oscillating modes, each vibrating with 0-point energy. And these vibrations aren't just mathematical curiosities, they have real physical consequences. So why does all of this matter? Well, because these fluctuating electric fields, even in the absence of real particles, can exert tiny forces on charged particles. Take the electron. It interacts with all of these vacuum modes. Each mode gives it a slight nudge, not enough to kick it out of the atom, but enough to gently jostle its position. And here's the point. Those tiny nudges add up. Each mode contributes a minuscule displacement, but summed together, they cause the electron's wave function to become slightly smeared out. And the result of this smearing is that its average position and its coupling to the nucleus shifts ever so slightly. And that shift leads to a small but measurable change in energy, and we call that shift the Lamb shift. Now, to quantify this energy shift, we will begin by estimating how much the electron is displaced by just one vacuum mode. In other words, how much does a single oscillating electric field mode with wave vector k and frequency omega k displace the electron? Once we understand the effect of one of the vacuum modes, we can then start thinking about the cumulative impact of all of them. Since the electron carries electric charge, it will experience a force from the fluctuating electric field associated with this vacuum mode, and this will be given by the electric charge multiplied by the field strength. And this force causes an acceleration equal to the force divided by the mass. And if we then sub in the expression for the force, we get the following equation. Now, it's important to note that for this approximation, we are able to neglect magnetic forces since the electron speed is much less than the speed of light. And so any magnetic interaction, which depends on the velocity of the charge, is negligible compared to the electric force. Now, the mode with wave vector k oscillates with angular frequency omega k, and therefore has time period equal to 2 pi divided by omega k. And therefore, the time taken for half an oscillation, which is the time over which the field is approximately pushing in one direction, can be written as the time period divided by 2. And if we then sub in the expressions for the time period and for omega k that we derived earlier, we find the result pi divided by c times k. Now, assuming the electron is initially at rest, we can calculate the displacement of the electron using SUVAT, namely, the displacement due to mode k will be equal to half times the acceleration times the time squared. And if we then sub in our expressions for the time and for the acceleration, and then simplify, we find the following purple expression. And then, if you recall the expression we derived for the electric field strength, and sub this into our displacement equation, we find the following green expression. And if we then combine terms and simplify, we end up with the following beautiful equation. And so we see that over half an oscillation, the displacement of the electron is proportional to 1 over k to the power of 3 over 2. Okay, so let's take stock. We've calculated the displacement caused by a single vacuum mode, one wave vector k, one fluctuating field. But the vacuum isn't just one mode, it's an infinite set, with one mode for every allowed value of k. And since these modes fluctuate independently, their effects on the electron are uncorrelated. To estimate the total effect on the electron, we sum the mean square displacements. In statistics, we say that we add in quadrature, squaring each contribution and summing, and so we can write delta r squared as the following sum. But how do we actually perform that sum? Well, earlier we placed the field in a cube of volume L cubed, which discretized the allowed values of the wave vector k. In k space, they form a regular 3D grid, spaced by delta k equals 2 pi over L in each direction. This regular spacing means that in 3D k space, each allowed mode occupies a cube of volume 2 pi over L cubed. So the density of states is L divided by 2 pi cubed modes per unit k space volume. Now, here's the key idea. As the box size L becomes very large, the spacing between adjacent k values becomes very small, and the discrete grid of allowed modes becomes dense. In this limit, we can approximate the sum over k by a continuous integral as long as we include the density factor L over 2 pi cubed to account for how many modes fit into each small region of k space. So to put this another way, in the continuum limit, we can replace the sum over k with an integral over k. This is how we go from a discrete sum to a full integral over all possible field modes. Then, because this integral only depends on the magnitude of the wave vector k, it proves convenient to switch to spherical coordinates by writing d cubed k equals 4 pi k squared times dk, and then we end up with the following integral expression. Next, if we take the expression we derived earlier for delta rk and sub this into our integral and simplify, we end up with the following purple expression. And we notice that the size of our box, L, has completely dropped out of our expression, which is what we would have wanted given that it was just a mathematical tool in the first place. Okay, so we now have an expression for the mean square displacement. At first glance, this seems promising, but there's a problem. The integral diverges. That is, if we integrate 1 over k, we find that the result gives infinity. In other words, the calculation predicts an infinite displacement, which is clearly unphysical. So what's going wrong? But before we fix the infinities, just a quick reminder to hit like and subscribe if you want to see more physics deep dives. It really helps the channel grow and reach more people. But now let's get back to it. This is where regularization comes in. The key idea is that not all vacuum modes can meaningfully interact with the electron. We need to impose physical cutoffs, both at the low and high energy ends, to restrict the range of wave vectors we include in the integral. Let's start with the infrared cutoff, which deals with very long wavelength modes, the ones with smallest k. If the wavelength of a mode is much larger than the size of the atom, the field varies so slowly across the atom that the tightly bound electron is barely disturbed relative to the nucleus. As a result, these very long wavelength modes do not significantly contribute to the energy shift. That's why we impose an IR cutoff at around 1 over A0, where A0 is the Bohr radius, the characteristic size of the hydrogen atom. At the short wavelength end, we impose an ultraviolet cutoff to exclude extremely short wavelength modes corresponding to large values of K. Why? Because once the wavelength drops below the electron's Compton wavelength, the energy becomes large enough to create real electron-positron pairs from the vacuum. That's a clear signal that our simple picture of virtual fluctuations gently nudging an electron no longer applies. Therefore, to stay within the limits of our low energy approximation, we exclude these modes by introducing a cutoff at K max is equal to 1 over lambda c, where lambda c equals h bar over mc is the Compton wavelength that we derived earlier. So if we now take these two cutoffs and sub them into our K integral and then simplify, we find the following result, involving the logarithm of the ratio of the Bohr radius to the Compton wavelength, and this gives us a finite well-defined expression. Now, we've already derived expressions for both the Bohr radius and the Compton wavelength, and so if we sub these into our logarithm expression and simplify, we find that the logarithm can be written as log of 1 over alpha, where alpha is defined as e squared divided by 4 pi epsilon naught h bar c, which has a numerical value of roughly 1 over 137 and is known as the fine structure constant. So now, if we put everything together, we find that the total mean square displacement is proportional to the logarithm of 1 over alpha, where alpha is the fine structure constant. This is remarkable. It links the quantum jitter of the electron, caused by vacuum fluctuations, to one of nature's fundamental constants. And as we'll soon see, it leads directly to an order of magnitude estimate of the Lamb shift. The key idea is that these fluctuations effectively blur the electron's probability cloud, reducing the average Coulomb attraction it feels from the nucleus. To see how this works, we're going to consider a visualization. We are going to consider a semi-classical picture of the electron inside a hydrogen atom and imagine it located at a radius a0 from the nucleus. Of course, in reality, the electron is not perfectly localized, quantum mechanics forbids that, but for the purposes of this heuristic model, we treat it as if it sits at the most probable radius a0 to estimate the effect of field fluctuations. We then suppose it undergoes a random kick due to the quantum fluctuations of the electromagnetic field, which causes a displacement of magnitude delta r in a totally random direction. It could nudge the electron either closer to or further away from the nucleus. We have, of course, exaggerated the size of the kick for the purposes of visual clarity. Now, to see the net effect of these random kicks, let's imagine our electron is sitting at the Bohr radius, and then let's draw a circle with radius equal to the average displacement delta r due to the random kicks. This circumference represents all the possible places that our displaced electron could end up as a result of one of those random kicks. To make things clearer, let's shade this region, and now let's imagine that it undergoes a random kick represented by the green arrow. As a result of this kick, the electron has moved further away from the nucleus. Alternatively, imagine the electron gets randomly displaced into the darker blue shaded region, as represented by the green arrow. In this case, the electron ends up moving closer to the nucleus. Now, we can clearly see from the two shaded regions that there are more ways that the electron can be randomly displaced, such that the distance from the nucleus increases rather than decreases. And due to this imbalance, the average or expected displacement ends up pushing the electron further away from the nucleus. To estimate the magnitude of this outward displacement, we can use dimensional analysis. The only two relevant length scales we have in this picture are the individual kick size, delta r, and the characteristic atomic size represented by the Bohr radius A0. And the only combination of these two that gives a result with the correct overall units of length is delta r squared divided by A0. We can in fact determine the constant of proportionality by running a simple simulation. To visualize this, let's consider a semi-classical simulation of the effect of these vacuum fluctuations. We represent the electron as being most likely found near the Bohr radius, and then in each frame it receives a tiny random kick, sometimes inward, sometimes outward. As these random kicks accumulate, we track the average change in radius over time, and remarkably, it converges to 1/3 times delta r squared over A0. This confirms that random, uncorrelated vacuum jitters tend to push the electron outward on average, weakening the Coulomb attraction and slightly shifting the atom's energy. In a fully rigorous treatment, this effect manifests not as a literal motion, but as a shift in the electron's wave function. So the natural question is, how big is that energy shift, and does it match what we observe in reality? To answer this, we need to consider the Coulomb potential felt by the electron. From the plot, it's clear that if the radial distance increases slightly, then the potential becomes less negative. The electron is less tightly bound. To quantify this, imagine the electron's radius increases by the average radial displacement. Then, as a result, the potential energy also changes. So, how do we handle this shifted potential energy function? And can we actually calculate the resulting change in energy? To do that, we perform a simple Taylor expansion to approximate how the potential changes when the electron is displaced by a small amount equal to the average radial displacement. Expanding the Coulomb potential around R and keeping only the linear term, since higher order terms don't significantly contribute, gives us a simple expression. The energy shift is approximately equal to the average radial displacement times the derivative of the potential with respect to R. This second term captures the effect of the electron's slight outward displacement on its average potential energy. To evaluate this, we simply need to differentiate the Coulomb potential with respect to R, and if we do that, we get the value E squared over 4 pi epsilon naught R squared. And if we substitute this into our expression, we find the following quantitative estimate of the energy shift in terms of the average displacement. Next, if we set the radius equal to the Bohr radius, A0, which is the most probable distance of the electron in the hydrogen ground state, we get the following shift in energy. Then, by plugging in our earlier result for the average outward displacement and simplifying, we arrive at a compact expression for the energy shift in terms of the mean square displacement. Finally, we substitute in the expression we previously derived for the mean square displacement, which, if you recall, involved the logarithm of the inverse of the fine structure constant, and by combining the two results, we arrive at this elegant final expression for the energy shift. Now, it will prove useful to rewrite this shift in terms of the magnitude of the hydrogen ground state energy we derived earlier, in which case we find the following green expression. And then we can neaten things up even further by using our expressions for the Bohr radius and ground state energy and then rewriting these in terms of the fine structure constant, in which case we end up with the following compact and elegant expression. And so, after the dust settles, we find that vacuum fluctuations of the quantum electromagnetic field cause a small but measurable shift in the electron's energy, a correction that scales with the fifth power of the fine structure constant, multiplied by the logarithm of its inverse. The result is a shift of order 5 × 10⁻⁵ electron volts, roughly a millionth of the hydrogen atom's ground state energy. Yet this tiny correction is a real and measurable consequence of the quantum vacuum itself. And the effect becomes even smaller for electrons in higher energy levels. If you repeat the analysis for the nth level, you find that the energy shift scales like 1 over n cubed. So for n equals 2, which corresponds to the first excited state of hydrogen, the correction drops by a factor of 8. This reduced energy shift corresponds to a frequency shift of roughly 1000 megahertz or a gigahertz in the radiation emitted during transitions between states within the n equals 2 level. And this is where history comes in. In 1947, at the Shelter Island Conference, one of the most significant gatherings in 20th century physics, Willis Lamb unveiled a puzzling anomaly. Using ultra-precise spectroscopy, he had found that the 2s and 2p energy levels in hydrogen, which Dirac's theory predicted to be exactly the same, were in fact split, corresponding to a frequency shift of around 1000 megahertz. In presenting this astonishing and unexpected result, Lamb laid down a challenge to theorists to explain what could be causing the shift. And that was exactly what Hans Bethe did on his train ride when he left the conference. In a burst of intense creativity, he scribbled a rough calculation that, astonishingly, came very close to the measured value quoted by Lamb. It was a turning point. Theory had finally caught up to experiment, and with that, a new chapter in our understanding of nature had emerged. The vacuum itself, far from being empty, could shift the energy levels of atoms, subtly, quietly, but most importantly, measurably. So, is the atom really empty? Well, if we're talking about nuclear matter, then yes, more than 99.99% of an atom's volume isn't occupied by the nucleus. But if we're talking about what actually fills that space, from the perspective of quantum field theory, then the answer is a definitive no. Because what looks like nothing is, in fact, something. It teems with activity. It's alive with structure, with jittering quantum fields that ripple even in the absence of particles. The vacuum is not a passive void, but a dynamic entity, one that shapes reality, shifts energies, and leaves measurable fingerprints on the hydrogen atom itself. Or, as John Wheeler put it, no point is more central than this, that empty space is not empty. It is the seat of the most violent physics. And on that note, I want to say thank you for listening, and until next time, goodbye. And as always, a massive thank you to all my patrons, and a special shout out to Felix, Bert Humberg, Lucas Mack, and Mike Purvis. Thank you so much.